Okay, so what I'm going to talk about is highly connected to the discussion that we had yesterday about the formation of the seeds of black holes, which is one of the major open problems in understanding supermassive black holes. So this is work we started a couple of years ago in a Nature paper, and then we're continuing in various ways to investigate a new model for the formation of massive seeds by what is called a direct gas collapse scenario. This is the densest slide of the talk. I'm trying to give you just a very brief introduction of what is meant by direct gas collapse formation of massive black hole seeds. In general, there are different flavors of this type of models. The idea of this model is to be able to make a large seed black hole of at least 10 to the 5 solar masses from the very start. And then this black hole will grow very efficiently, even if it's not growing at Eddington all the time. It will easily reach the masses required to explain the highest quasars, as long as you can do this head start seed formation a sufficiently high redshift. And as we said yesterday in the discussion, in that more conventional model in which you try to explain all the supermassive black holes by growing very light seeds produced by the collapse of POP3 stars, so you start with very small masses of about 100 solar masses for the seed, explaining the big bright quasars at high redshift is very problematic, because all the numerical models show that these POP3 seeds grow very, very well below Eddington, will never reach the required masses by a redshift 6 or 7. So trying to explain the high Z quasars is one of the main motivations to start with a very big massive seed. Now, how you can do that? Well, the first thing that you have to care about is losing efficiently angular momentum in the gas component of your protogalaxy. You want to be able to pile up at least a mass comparable to 10 to the 5 solar masses or more. In a very small region. Of course, it would be very below parsec scales, because you have to produce a very compact precursor that will eventually produce the big black hole by dynamical collapse. So the first stage of the process has to involve losing efficiently angular momentum in a protogalaxy from kiloparsec scales to scales well below a parsec. Okay? Well, the actual scale depends on the particular flavor of the model that you're thinking of, but you have to get to an object that is probably 0.01 or 0.0 or even less than that in parsecs. There are more flavors. So you can think of mainly two pathways. You can think of forming first a supermassive star. That's actually the second way. And the supermassive star, which will be very short-lived, 1 mega here or so, will eventually collapse into a massive seed. How it does collapse into a massive seed is subject of a lot of theoretical work at the moment, mostly by Mitch Begelman and collaborators, where they envision that you might have a transitory phase in which only the very center of the supermassive star collapses into a black hole, but the rest behaves like a radiation pressure supported envelope, which accretes onto the seed at a super Eddington rate for the envelope and gets you to a 10 to the 5 solar mass seed on a time scale which is less than 1 million here, so essentially very short. The other possibility, which is more popular among the numerical GR community, is that if you're able to form a supermassive gas cloud of, say, 10 to the minus 2 parsecs containing about 10 to the 6 solar masses of gas, and this cloud has only weak rotation, it could undergo a radial post-Newtonian instability and collapse directly into a black hole without even forming a supermassive star. And that's work that has mostly been explored with numerical GR simulation. There's recent work also by the Japanese group that shows that if the angular momentum is not high, you can actually have an outcome like this, just for pure dynamical collapse of a cloud with sufficiently low rotation and very high mass. Now, I'm not talking about the second stage, so how you can actually get to the black hole itself. But I'm talking mostly about number one. So is there a way that you can pile up gas into a supermassive gas cloud well below parsec, starting from the gas that you have available in a protogalaxy? Now, one important point to keep in mind when you're trying to form a massive seed is that either for example, in the case of the supermassive star scenario, you want to be able to assemble this object and so the precursor of the supermassive star as well, on a time scale that is at least not longer than the lifetime of the star, right? Otherwise, it would be not self-consistent. So that gives you already a limit on the mass inflow rate that you need to have to assemble the cloud that will produce the star. That's basically related to the mass of the star divided by the lifetime, gives you a minimum inflow rate for a star of 10 to the 6 solar masses of 1 solar mass per year. So you have to pull gas inward at least at this rate if you want to make a supermassive star of 10 to the 6 solar masses. Now, let me just, okay. How do you do that? Well, a typical scenario that a lot of people have explored is relying on gravitational torques at the scale of a protogalaxy. So suppose you have a very dense gaseous protogalaxy, and this undergoes a phase of gravitational instability. It forms very strong spiral waves. These spiral waves are well known to be an efficient way of redistributing angular momentum, removing angular momentum from the inner regions and transporting outward. And you typically end up with a more concentrated gas blob at the center, and that could be a way to produce a very dense condensation at the center of a protogalaxy. However, there is a caveat here that in order for spiral waves to be efficient at doing this, you need a disk that is unstable but not too unstable. If the Toomery parameter of the disk gets low to about 1 or less, then you will undergo fragmentation. And you enter in a completely different regime, no more spiral waves, you have clumps, you have star formation if you want. So you will use your gas to form stars rather than to produce a central condensation. So the general problem here, which has been looked at in different ways in the literature, is to be able to remain in this regime for a long enough time to pile up enough gas at the center while not undergoing fragmentation and star formation. How you do that? You have to keep your Toomery parameter large enough. And that means one way is if you have a very massive gaseous disk, you cannot play with the mass of the gas. You want to have a lot of gas available. You can play with the temperature. You make it warm enough that the Toomery parameter never gets close to 1. How you can do that? Well, you have to suppress the coolants that are active at the protogalaxy level. And so you have to suppress molecular cooling and metal cooling. That means that it's a scenario that might work when you have gas that is mostly still at primordial composition, and you need to dissociate H2 in some way so that it doesn't lead to cooling as well. So you have to force the system to avoid cooling, essentially, which seems a bit difficult. And in fact, there's no convincing model that proves that can happen in a realistic condition. Right? As long as you have some metallicity, the gas will start cooling. Even at redshift of 15, the metallicity usually in simulations is large enough to allow some cooling and go from this situation to this situation. Okay? You can dissociate H2 by relying on, for example, forming this protogalaxy close to a much bigger system that shines with strong Lyman-Werner flux. But again, that would be a very special condition. You need to have a very particular local environment. And again, it wouldn't fix the problem of having some metals that still produce some cooling. Then there is also another problem. Even if you just do say a dock model, you suppress the cooling, you don't ask how you can do it, but you just shut off cooling, you remain in the situation. Then you can look at the gas inflow rate that you get in simulations that do this. And the inflow rate is typically smaller than this 1 solar masses per year. That is the minimum that you need to get to this supermassive star precursor. So either you never remain in this condition, or if you do, you never get a sufficiently high inflow rate. So there is, of course, another situation in which very strong gas inflow rates can occur, even at low redshift, even in normal conditions. We know that. It's mergers. In mergers, we know that there are very large inflow rates of gas of more than 100 solar masses per year. In the case of Ulrichs, for example, this has been found in a lot of simulations that are trying to explain the origin of Ulrichs or submillimeter galaxies through mergers. So it's no news. And we know that in mergers, although it's a situation with a very high star formation rate, still most of the gas doesn't form stars. The efficiency of star formation, even in mergers, is never above 10%. This is something that we had discussed also in the previous days. So then it tells you essentially that the gas consumption timescale into stars, if the inflow is occurring on a dynamical timescale, that gas consumption timescale is longer than the inflow. So as long as you have a strong inflow, that inflow will keep going. The point is, will it keep going to very small scales, will just stop at, say, 100 parsec scales, the typical scale of a starburst. Or you would be able to keep going to, say, 0.01 parsecs and have gas piling up at such small scales. This is the question that was not answered before, and that's what we try to do. We try to look at whether in mergers you can continue an efficient inflow from 100 parsec scales down to scales well below parsecs. So the way we did it is using SPH, but it's not particularly crucial here. Indeed, with Romain, we are redoing something along the same lines with Ramses, although for a different application. The main point is we take an idealized case just to look at the scenario as a proof of concept. If you take a major merger of two gas-rich protogalaxies and you use particle splitting of SPH to increase the resolution so that you can resolve 0.1 parsecs scales in a merger that is in a volume of several tens of kiloparsecs, what do you actually see? Well, let me say, and I can talk about this more if people are interested, we have to decide what we do with the gas thermodynamics. We are spanning a high range of densities, and it's unfeasible to think of doing self-consistent cooling and heating at all scales with radiative transport and so on. Eventually, we will have to do that. But we started with a simple model. We use an effective equation of state, which is based on a Spans and Silk model, which was calibrated with radiative transfer calculations. And it's basically an equation of state that works, is supposed to work for describing the balance between heating and cooling in a starburst, which is what you expect to happen in a merger like this. So you have star formation built in your thermodynamics. So it's not something that we want to avoid here. We want to have it because we are trying to deal with a situation where you expect to have a high star formation rate. That's a major difference with the philosophy of the previous direct collapse model. So what happens when the galaxies collide and you're able to keep following what the gas does down to scales of less than a parsec, that's what you see. So imagine that the two galaxies are colliding, as in typical merger simulations, on scales that are galactic, but then you zoom into the inner hundreds of, this is about 200 parsecs box size. You zoom in central 200 parsecs at the time of the final collision of the two galaxies, and that's what you see. You see a very strong M=2 mode forming, which is obvious because that's due to the geometry of the merger, which is, it's essentially imposed by the perturbation due to the merger. And very rapidly after the collision is over, so we're talking about very short time scales here, 10 to the 5 years after the collision is over, you see the formation of an unstable circumnuclear disk. It's born unstable because it's formed in a perturbed condition, and the disk drives a secondary inflow, which is what we were hoping to find, that produces, via spiral wave transport, an efficient gas condensation at the center. And when you zoom in at the scales of less than a parsec, you see the formation of this very massive cloud, which is Jensen stable, and keeps collapsing until we reach the resolution limit, essentially the softening, which is of order 0.1 parsecs. The SPH resolution is much higher. We have about 10 to the 5 particles inside this cloud. So the hydro is extremely well resolved. We are limited by the fact that the gravitational softening is 1.1 parsec. We cannot say anything about the further collapse. But until that point, this very well resolved cloud just keeps collapsing because the Jensen stable. Of course, we can't say anything about what will happen, but it's the first case where one sees the formation of a huge bound sub-parsec scale cloud. We are talking about 10 to the 8 solar masses on this scale, so it's really huge. And so the next step will be to see what happens. But this is a very encouraging situation for thinking of this as a precursor of a massive black hole seed. It's very hard to think how you could stop the collapse. The cloud is very hot. The effective temperature is about 10 to the 8. So star formation will not happen here. What could be a problem here is the fact that using the effective equation of state, you're certainly missing the fact that you have a multi-phase medium here. And so it might be that the formation of a cloud in a realistic multi-phase medium would be different. So that's something that one has to keep in mind. But the point here is that when the cloud forms, it does so because the inflow rate in the disk is huge. It is about 10 to the 4 to 10 to the 5 solar masses per year. You will never come up with star formation rate higher than that. The interesting thing is if the cloud collapses at least 10 times more in scale than what we can follow here, you get to the situation where it could really undergo this post-Newtonian instability. Okay? So that's possible that this cloud will not have to go through the supermassive star phase, but will directly collapse into a black hole. And that is something that we are now trying to do with numerical GR collaborators that are going to port the final condition of this cloud into one of their codes. Now, if this cloud, it's more than 10 to 8 solar mass, even if you take less than 1% of the mass of the cloud and you say that this will form a black hole, you have a black hole seed that is exceeding 10 to the 5 solar masses. In our model, we do this merger at redshift 8. We took the condition of, say, the highest sigma peaks that you have at redshift 8. So these are galaxies that are live in 10 to the 12 solar masses halos at redshift 8. So very high sigma peaks, as you expect for IZ quasars. So from redshift 8, this process that we simulate takes less than 10 to the 8 years. So extremely fast overall, from the merger time of the galaxy up to the formation of the cloud. So you have all the time you want to produce the seed fast enough to then grow and form one of the bright quasars. Now we looked at different conditions. So if you change, for example, the masses of the galaxies, what happens? The interesting thing is that this process seems to work only down to 10 to the 11 solar mass for the halo mass. So when you go to a lower mass, what would be a big dwarf galaxy if you want, it doesn't work anymore. And the reason is that the inflow is not self-gravitating enough as you lower the gas surface density in absolute value as you go to lower masses. It's not self-gravitating enough. You produce, of course, a density peak, but this is not a self-bound cloud. So we predict that this process only works for the most massive halos. So then the recent thing that we did, and I'll try to finish up very quickly, just showing you some of the results that we are putting together in a new paper, where what we did is we tried to explore the consequences, the statistical aspect and the implications of this scenario, provided that it will happen inside a large cosmological volume. So what we did is we constructed a new recipe for black hole formation based on the results that I just showed you, and implanted that in the Munich semi-analytical model in the Millennium simulation. That's work that postdoc Silvia Bonoli has been developing in the last year or so. So in the model, we keep the standard way of forming black holes that they had already in the Munich model, so based on the POP3 seeds. But we also include our direct collapse route. So we also implant 10 to the 5 solar masses seed in galaxies that undergo a set of conditions which are the ones that we found in our simulations. So it's not an ad hoc model, but it's based on the simulation. And these are the conditions. There has to be a major merger of a gas-rich late-tide disk galaxy, because the galaxies that we use in the simulation are disk-dominated. Otherwise, you will never have a sufficient strong inflow of gas, because you never form a thin disk at the center of the merger remnant. The host halo has to be larger than 10 to the 11 solar masses, and there has to be no pre-existing black hole of 10 to the 6 solar masses formed by another mechanism like POP3, because if you have that, the accretion energy of that black hole will eat up the disk. The feedback will eat up the disk and stabilize it against the inflow. Okay? So these are the conditions, essentially. So the process self-regulates in the sense that as the cloud gets large enough and the black hole grows, at some point the black hole disperses the cloud due to its own feedback. Okay? So there's a self-regulation built in the model. Now I just want to show you a couple of interesting results that we find. The first result is that although this mechanism, for the way we build it in the model, happens primarily at high redshift, this is the fraction of direct collapse seeds that we form as a function of redshift normalized to the total. You see, most of them are actually happening at redshift larger than 4, but there are some that happen even at low redshift. So the prediction of the model is that you should have also some galaxies undergoing this formation route at low redshift, because the conditions that we need in some rare cases happen also low redshift. And I'll show you what kind of galaxies these should be in terms of their environment. So the size of the supermassive cloud that we have in the simulations might be very dependent on the details of the thermodynamical model that we are using. So we wanted to keep it as a free parameter to see what happens if we change it. So that's what we find in our simulation, that we collapse down to 0.1 parsecs. But you could imagine that a previous feedback might produce a more loosely bound cloud. So we are exploring different sizes of the cloud that makes the precursor of the black hole. And you can see the mass functions in the different cases for the POP3 and the direct collapse seeds. Just look at the red and green lines, and you see that a higher redshift, the direct collapse seed dominate the mass function of the black holes. And when you get to redshift 4 or 2, depending on the model, the POP3 seed become more important. So low redshift, the POP3 seeds will always be statistically more important, but the high redshift population is dominated by the red ones, which are the direct collapse seeds. Now, the interesting thing, and I'm stopping here, is that if we look at which galaxies undergo direct collapse very recently, less than redshift 0.1, you can look at many properties of this galaxy, but one of them is the clustering properties. And interestingly enough, these galaxies, these are described by the red lines, they have and the green ones are major mergers that do not undergo direct collapse, maybe because they have a POP3 seed which is strong, big enough to stabilize the disk. And the blue one is the complete sample of galaxies that have the same stellar masses that we are picking in this red sample. And you see that the red sample undergoing direct collapse at low redshift is less clustered than both the general major merger sample and the overall sample of galaxies with the same mass. So these are these recent direct collapse events happen in objects that are fairly isolated because they're objects that essentially never had a major merger until the point where the first major merger produces the inflow. So then the interesting question is to look at where they should live, what kind of galaxies they should live in. And we are looking at that now. It seems they should live in early type spirals, essentially. So there are many other implications I couldn't discuss here. Let me just lay out some of them. Another implication, which is sort of obvious for all direct collapse scenarios, is at the very time when you form the massive seed, you expect to have a high deviation from the local M-black hole and bulge relation. Okay? So if this model is happening in nature, you expect to see that, especially at higher redshift, you should have many galaxies that have a black hole which is much higher than what expected by the local M-black hole and bulge relation. But again, because this happens also in some rare cases at low redshift, we should see some of them happening even at low redshift. Some there's very high offsets from the black hole and bulge. The point is how many, and this is what we are looking at the moment. Now, and talking about possible observational predictions, if the formation of the seed goes through this quasi-star phase, there is an interesting prediction by Volontari and Begerman that you could see some of these quasi-stars in JWST fields because they would emit like a black body at a few micron temperature. And a JWST should have typically 5 per field of these objects. So they should be detectable if they happen. Again, we don't know if our supermassive cloud will get there, but we are working also with Mitch about matching looking at how the conditions in their model compare to what we find in our simulation. There seems to be some similarity in the properties of the cloud and the initial condition of the quasi-star that they have in their model. And I think an important point is it doesn't work in low mass galaxies, meaning below 10 to the 10 solar masses. That's probably a strong conclusion, I think, because even if we use this simple equation of state, we know from what has been said by many people here that low mass galaxies have outflows, have very strong outflows. So in that case, you expect stuff to go out and not to go in. So it's sort of expected that if you want to have an efficient way of piling up gas at the center, you never have this in very low mass galaxies. And I will stop here.